Hello everyone, I'm Zhixian from Arizona State University. I will present our ICML 2025 work on robust reward alignment with hypothesis-based batch cutting, or HSBC. In the deployment of one reinforcement learning agent, reward design can be a difficult problem. Preference-based reinforcement learning helps you solve this issue by learning a reward model from human preferences. However, human preferences are inherently noisy, and the error may exist in the data collected. In BPref benchmark paper, we observe up to 20% of performance downgrade with only a 10% error rate in human data. There are some recent efforts trying to filter those false feedbacks in the data. However, those methods may require prior knowledge or introduce additional computation overhead. So in this work, our target is in twofold. First, we want a certifiable human data efficiency in the process of reward learning, and we also want provable robustness. We need to achieve this without explicitly identifying the human error. To achieve this, we can first introduce the concept of hypothesis space, which means the space of reward function or reward parameters, and it contains the implicit human intent θ. If we want to search for the θ in the space, we can use preferences to induce cuts and remove all of the hypothesis space portions which are inconsistent with the preferences. When a human gives a trajectory preference pair, actually he or she is giving an inequality that the intent reward must satisfy. And a cutting set based on this inequality can be built. To update the hypothesis space, we can intersect the old hypothesis space with the cutting set, and finally we get a new one. For scalability on the batch data, we can use a batch of preference to vote and update the hypothesis space based on the vote function, which is defined as the number of satisfied cuts for any given reward function theta. For example, we gradually incorporate cuts in one batch, and the total number of cuts is 3. The vote function of the different portions of hypothesis space changed accordingly. Finally, if we use the batch size 3 as the threshold, we can get the intersection of all those cuts. The major problem in robust learning is error data in one batch can mistakenly cut out θ. For example, when we repeat the batch cutting on previous slide and flip the direction of the third cut. If we still use 3, the batch size, as the threshold, we can end up cutting out θ, which means the learning is a failure. However, if we choose a lower threshold of 2, it's possible to preserve θ in the update. More generally, with batch size of n, we can choose a conservativeness level parameter gamma to control this threshold. This process is probably robust and error agnostic because we can include human intent in hypothesis space at all the time, and there's no need for explicitly detect the error preferences. The implementation of our proposed hypothesis-based batch cutting, or HSBC method, consists of 3 steps. The first one is to sample an ensemble of reward model from current hypothesis space. To do this, we can perform optimization-based sampling using the vote function. The second step is to perform trajectory planning and querying. More importantly, we only query preferences pairs, which have high disagreement among ensemble members. The third step is to update the hypothesis space using the batch cutting with conservativeness as discussed in previous slide. Here, we show results on 2 standard reinforcement learning tasks, cut poll and walker. In both tasks, HSBC still performs well under high rate of human error. These advantages also hold across different domains. For example, in-hand object manipulation and robot locomotion tasks with higher degree of freedom. HSBC is generalizable and works well across different tasks. To summarize, HSBC is a simple, interpretable, and effective method for robust reward learning from human preferences. Thanks for your attention, and please check out our project page.